Hi everyone and welcome to the sixth video of this series. So I finished the last video with the DC Josephson effect, and till now we had assumed that there was a zero potential difference across the Josephson junction. In this video, I'm going to consider uh, the case when the potential difference is not zero. So from the previous video, if you recall equation 1 and 2, I'm going to rewrite them for you now. Now, if you remember from the previous video, we had actually compared the real and the imaginary parts of these two equations. So if you now notice the imaginary parts, if you compare the imaginary part of both the equations, it will not change. So the expression of the current will remain unchanged. However, for the real part, we will get something different now. And I'm going to compare the real parts of both these equations and write them down. Now I'm going to assume what we also assumed in the previous video, and that is both the densities, that is rho1 and rho2, are equal. So I'm going to assume rho1 equal to rho2. And if we now subtract the top equation from the bottom equation, what we are going to get is the time derivative of the phase difference that will equal 2 EV over h bar. And this is actually the time derivative um, of the phase difference. So we have kept the voltage constant. So the potential difference is constant. So we can write the phase difference as follows. Now, if you recall the expression of the supercurrent from the previous video, it was, and if I now substitute the expression of the phase difference here inside the argument of the sign, this is what we get. And notice that I'm calling this entire constant that lies outside the sign, I'm going to call it as I naught for brevity. And what this expression suggests is that the current now is an oscillating current. And it oscillates with the frequency that is given by omega, which is 2 EV over h bar. And this is known as the AC Josephson effect. That is, the existence of an oscillating current is called the AC Josephson effect. Now, to summarize the working of this new element, I'm going to write the two key equations. So the supercurrent is related to the phase difference um, in the form of a sinusoidal relation, and the phase difference, the time derivative of the phase difference, is given by 2 EV over h bar, and V is the potential difference across the junction. Now, next, I'm going to calculate the work done by an external source to make a current IS flow through the junction. Notice that while writing this final expression here, I have assumed that the phase difference delta is 0 at time t equals to 0. Now further, I'm going to call the constant outside, that is this quantity, I'm going to call it E naught. Next, I'm going to write the expression of the inductance that is offered by the junction. And I want you to consider the time derivative of the supercurrent, that is dis by dt. And this is actually the derivative of I naught sine of delta. And I can write this as I naught cos of delta times the time derivative of the phase difference. And the time derivative of the phase difference is known to be. Now, if I look at the equation V equals L di by dt, I can write the inductance as V over di by dt. And from here, we get the value of inductance as. Now, I want you to notice that the value of the inductance that is offered by the Josephson junction can be indeed negative, or it can also tend to infinity because there's a cos delta sitting in the denominator. So if cos delta approaches zero, the value of the inductance can approach infinity. And this is the remarkable thing about this circuit element. Now, apart from the supercurrent, there can also be other contributions to the current of a Josephson junction. So, for example, there's a chance that Cooper pairs break up, which cause current to flow due to the flow of single electrons only. Uh, and so this is like a normal current which flows in a conductor. That is due to the flow of single electrons. And single electrons, while flowing through a superconductor, they are often called quasi-particles in such a situation. I'm just going to write briefly what I just stated. And so this so-called normal current, as it is known, it is given by I with a subscript n, and I can write this as Gn times V. V here is again the potential difference across the junction, and Gn is the conductance, and this conductance often depends on V itself. Now, apart from Is and In, there's also a third contribution to the junction current, which is due to the capacitance. So notice that the Josephson junction consists of two blocks of superconductors separated by a thin insulating barrier. So as you know, such a structure often leads to a capacitance. So the Josephson junction has also a displacement current flowing through it because of the presence of this capacitance. Now I'm going to denote the junction capacitance as C, and so we can write the displacement current as simply C dV by dt. And from the above three types of current that we have mentioned, the total current flowing through the junction can be written as. And you can go through how I wrote these expressions for IN and ID. I'm not going to go into that because it's really straightforward, so I'm going to skip it. You can go through it yourself. Also note that for brevity, I have written the uh, Josephson junction as just JJ. So this so looking at the current equation, we can actually represent this circuit element through the following equivalent diagram. Also, just like we calculated the energy stored in the junction, there will be an additional energy that will be stored in the capacitor. So I'm going to now write the additional energy that is stored in the capacitor. And if you remember from before, we had written the energy stored in the junction as E naught times 1 minus cos of delta. Now I want to write this energy in terms of E naught. So I'm going to define a plasma frequency. And so we can write the energy stored in the capacitor as follows. Also, to recall, E naught is actually h bar I over 2E. So now we can write the total energy that is from the junction part alone, as well as the capacitive part of the junction. We can write the total energy as follows. And I want you to note one thing, that this energy expression is valid only if we take the resistance, that is 1 over Gn, to be quite small. So it should be sufficiently small so that almost no energy is lost as heat. So this expression is only valid uh, when the resistance is very small. I'm going to end the video here, and in the next video, I'm going to demonstrate an analogy of this circuit of the model which we came up with a mechanical model. So it will help us understand the circuit element more intuitively, and you would also understand why I defined this plasma frequency. So at first, this seems like an arbitrary expression, but once I make that analogy, it will be very clear to you why this quantity is significant and why we defined it in the first place. See you guys in the next video.